Morning, everyone. Before we start, just a few general comments. The third programming assignment is online now, or online since the end of last week. I hope you already saw it. If not, be aware that the deadline is relatively soon. The original plan was to have like 4 weeks for the second assignment and 3 weeks for the third assignment, but the second assignment got a little longer because of the vacation week. So don't underestimate it, or be aware that the time for this assignment is shorter than the time for the last assignment. And also, because if you already looked at it, we phrased it now that you can choose from certain tasks and you have to do 5 of the 6 easy tasks to get an 8. That can, of course, be a little misleading for some people. Easy is a relative term, so it's from the tasks we listed, those are the easy ones, but that doesn't mean that the tasks themselves are easy. Some of them are should be quite simple, but don't underestimate the time it takes. And yeah, also from the style is a little different. You probably saw it, that we have a list of different things where you can pick from. We thought it's a nice idea at the last practical to have something where you are a little more flexible, so the people who are beginners still have a chance to get a good grade, and also the people who are more experienced have a possibility to like do a little more and get a little more creative. So there are a couple of also very hard tasks which are not really that clearly specified. So if you have questions with them, if you want to try one of the hard tasks or the medium tasks, and you need more information, just contact the teaching assistants. Or if you want to do something in a special way, because they're not that clearly specified, it could also be that you do something for the hard task that is kind of, only solves half of it, or is only a little small part of the actual solution. And then if you're unsure, this can be a little irritating for you. Then you don't know, is that enough, or do they expect more or so? In such a case, just go to the teaching assistants and ask them, and they can give you information. And in any case, if you're in doubt if what you have programmed or what you want to turn in, or what to turn in, for example, if you do a little more and you want to turn that in, or if you have a little less, then just ask the teaching assistants, and also make always sure that what you do is specified in the README file that you send. Because think about, we have almost 200 students this year, so if they do the grading and then they don't have time to look into detail and guess what you did. So it would be kind of a pity if you do some really nice extensions, but they are not really looked into because they just didn't see them, because you just didn't note them. Yeah, but if you specify that, then we will check. It will work out even if you do like more or a little bit less, because I mean, in the end, we use software to check if you copy and paste stuff, but we do the grading not by software but by humans. So as long as you specify everything and get in contact with them, it should work out. There is a little because we have these different tasks, it's a little fuzziness. So for example, you could do 5 easy tasks and then decide to do 1 medium task, and then after a while you realize, well, we're not going to finish that medium task, it's too difficult for us. Maybe we start with another medium task, and then when the deadline comes, you have 2 medium tasks half solved. So it's kind of critical then how to grade this. But if something like that happens, talk to the teaching assistants, and then they tell you, then most likely write it in a README statement and then turn in what you have, and then we will see how we do this with the grading. Yeah, so like I said, we do this the first time, so we will see how it works out. Those who are a little more experienced and want to do more, you're also welcome to do other stuff. If it's not on the list and you have some complete weird idea and want to do it and just want to show it, or just want to submit it, it's probably better not to submit it, but get in contact with the teaching assistants and meet with them during the sessions and get feedback from them. Like I had a question from someone who wanted to do some stuff that was not on the list, but and he said that's fine with me if I don't get a grade for it, but I just would like to have some feedback on it. You're very welcome to do that. it's probably better not to do it in the assignment because the risk that it gets screwed up with the other stuff is a little too high, and it makes it more difficult for us to grade it. So it's probably better to get in touch with the teaching assistants, and I will inform them about this. So if you do something really exceptional, there is also a way that we kind of informally consider it in your grading then in the end. All right. Other comment about the practicals: if you change your group because your partner gets lost, or because you have a 3 group and you want to split up and join another one, it's usually not a problem. Just make sure that you inform me about it so I can update the lists that I have and we don't run into problems later, and we don't we just want to make sure that everyone contributes to all of the groups and that we don't have situations where one guy just puts his name on it. But other than that, if you want to switch groups or form a new group, that's okay. Just let me know about it so I can update my lists. The grading for the second assignment will take a little longer. Sorry for that, but there have been some problems with that and some delays, so it just will take a little bit longer. But if you have a question related to that is also that you want to have answered, or that is important for the third assignment, for example, if you say to do that, I really need to know if what I did before is correct or so, then don't hesitate to contact the teaching assistants about this, and they are willing to help you. I mean, you turned everything in now, so there is no point in not giving you the solutions to it. But you have to get active yourself. You have to ask them. All right. What else did I miss? Yeah, here I already announced this, but for the second and also for the third assignment, we will also make some random group checks. So we will just randomly pick a couple of groups and then schedule a meeting with them where they have to show us their code. This is basically just the problem. Normally we should do this with every group to justify to check that everyone really contributes to the group, but with 200 people we just cannot do that. So we do this kind of random check already. Last year we did it like that and it worked out quite well. So but don't be surprised if you get an email, yeah, you have been scheduled to a meeting with the teaching assistants to check your code. This does not mean that we think you cheated or so. It's just really a random check. So no need to worry. And what we want then is basically that, like I said before, when you have a team, that every member of the team should have a high-level overview of the whole code and know more about the details, of course, of the part he or she has done himself or herself. So normally, if you participated in it, then in the programming, and did not copy it from your partners, then there is no need to worry about it. Good. So I will inform you probably by the end of the week, the teams who are affected, by email. All right. Are there any questions to this organizational practical stuff? No? Good. Then we can start with the actual content. So today we will continue with the graphics pipeline. The graphics pipeline, you probably remember, this is the so we're in the 8th chapter of the book now, which is called the graphics pipeline, and this is an image of that chapter, which I already had in the first lecture to give you a little an overview of it, and also because you kind of needed to have the terminology because of the first practical assignment. But now hopefully we're in the process now of understanding what these things mean and how these algorithms behind those things work. So for example, for the vertex processing, which is mainly the process of putting the 3D image onto a 2D projection in a perspectively correct way, we learned two lectures ago that we can do this by matrix multiplication, by using first a matrix to move from the world space to the camera space, because that makes then later our projection much easier. Then we learned how to do a perspective transformation to move everything to the orthographic view volume, which again makes the projection much easier because it reduces the problem to an orthographic projection. Then we did a scaling to the canonical view volume, which again makes it easier. And then in the end, we have a 2D image that we just need to scale to the actual screen values or window values of the window where we want to show our graphic in a so-called windowing transformation. We saw that by extending this matrix format, by extending the notion of homogeneous coordinates, we saw that we can do all this with matrix multiplication. And then last time we basically continued into looking into what is going on in this graphics pipeline, because this projection works fine if all the triangles are within the so-called view frustum, which is basically the area or everything that the camera can see. But if they are outside of the view frustum, of course we will not see them in the final image, so it makes sense to not process those because it would be a waste of resources. So we remove them in a process called culling, and the triangles that are partly inside of the view frustum, we have to do some clipping because we have to cut off the part that we cannot see. And this is, in this case here, it is pretty much just for efficiency, because we don't need to do that. But we had a case here where we had an example here where we had a triangle like this. And then we saw if we do not do a clipping, then it will have some problems with the projection, that we will actually see the triangle at the wrong position because there is this change at the z-axis from positive to negative. Yeah. And then we also talked about if we have triangles that overlap each other, objects that overlap each other, how can we make sure that we are drawn in the right order, and we introduce this so-called set buffer that helps us in doing this, which is usually a hardware support, although there are also software solutions for that. And then we already talked about in an earlier lecture about texturing, and a little bit about shading, which is then basically putting some color onto those triangles so they look realistic. But the one thing that is really missing so far is how do we get from the geometry to the actual pixels, and that is the process, the so-called process of rasterization. So we have a projected 2D triangle now, but it is still like an abstract model in a screen space. But what we really want to have is really the pixel information. If we have a screen with pixels or window with pixels, we really want to know which of the pixels do we have to draw in on our window. And this process is called rasterization. Now, this pretty straightforward approach for this would be, of course, we say we have the four corners, the three corners of the three vertices of the triangle. And we want to know now which pixel is inside of the triangle, because that's a pixel where we have to put the color on. And then we can, of course, for example, check each single pixel here and see, is this part of the triangle? And if it is, we draw it, and if not, we draw it not. But of course, you can imagine we do this for each single triangle with a very complex model with thousands of triangles. We have to go over the whole image 1,000 times, so that's pretty stupid and doesn't not very efficient. The first simple trick we could do is, for example, just look at the bounding box of a triangle, and the bounding box is basically defined as the minimum axis parallel box that completely includes an object. And there is a very simple way to calculate this, which is by this formula here. So if we have a 2D case, then this is the way how to get it. In a 2D case, we can describe a box by 2 points, a lower bottom point and an upper right point, and that way we have defined a rectangle, and that bounding box is now the smallest rectangle that contains the whole triangle. And we get these points here, B0 and B1, by just looking at the minimum and the maximum value of the edges. So we see here, if we start at that edge, for example, this here is x1 and y1. So these are per default the minimum values. So this is x1, y1. And then if we take the next one, which is then x2, y2, we see that, and they were also the maximum, of course, but now we see that the maximum becomes x2, y2, the minimum stays the same. And if we continue to the third edge, we see to the third vertex, we see this is x3, y3. So we and we see that the y value is larger than the minimum but smaller than the maximum, so that doesn't change. Whereas the x value has a larger maximum, so this here gets replaced by x3. So our final corners of the bounding box are x1, y1, which is the minimum, the lower left value, and the maximum value is x3, y2. So pretty straightforward and pretty simple, you see, and that saves us a lot of checks, checks, of course. Yeah, but still, of course, if we have a triangle that is not, or if the bounding box doesn't really match very well with the shape that we want to check against, then we still have to do, like in this case here, we still have to do a lot of really useless tests here, and that still costs us a lot of processing time. And the situation gets even worse if we're not dealing with triangles, but if we're dealing with random polygons, because then, of course, we can have something like this here. Polygon like this, where we have, so this should be straight lines. But then you see here with the bounding box we get huge areas where there is nothing. So we're interested in a more efficient way to do this, and this is an algorithm now to rasterize general polygons. So we look at the general polygon now, like in this example here. And now you remember, if you look at the image, you see that the pixel here is in the center of the grid. You remember we had this when we did the I think it was the windowing transformation, that we said that a pixel is always to the center. When this is like the integer value, so this is, for example, I, and this is I plus 1, and that is why we had to in the matrix we made a minus 1/2 or minus 0.5 to get from this point here, which is the integer value, to the actual center of the pixel. And in this case, so this is why it's drawn here also in the center of this square. And to make our calculation and the explaining easier, we just take it and just move it a little bit. And yeah, so this is just a convention now that I'm making to make the writing easier, because otherwise I would have to write 0.5, 0.5, plus 0.5, plus 0.5 after every value I'm writing. So this is just to make our writing easier, or life easier. Good. So the algorithm that we're using for this is a so-called scanline conversion algorithm, and the idea of a scanline algorithm is basically that we have a line that we scan over a window, and while we are moving that line over a window, we do some operations with the objects that are passed by the line at this particular moment. And one important characteristic of scanline algorithms is that all the operations that we're doing at a specific time at this scanline only depend on the data that we have seen so far, but not on the data that is about to come. So if we have, for example, a rectangle, assume that's a rectangle, and this is our scan line, assume that's a line, moves to the right, then we do some operations at the scan line here, and those operations can depend on all the parts that the scan line has seen so far, but not on the parts it hasn't seen so far. We could also have a scan line that moves up, or we could also have a scan line that moves like in a more diagonal way over the window. But in any case, the operations that we do on the scanline only depend on the past, and the result of this is, of course, that we just need one scan over the window and then we're done, which is why the scanline algorithms are usually quite efficient and quite effective. So if you study geometric algorithms later in your studies, if you take that course, I'm pretty sure they will have a couple of scanline algorithms or related algorithms there. So in case of the polygon rastering, we take a scan line that is horizontal and move it up. And now you see here it says it takes advantage of scanline coherence. That is basically means that it depends on the previous values and takes advantage of those values. So in general, techniques that take we talk of coherence when we have techniques that take advantage of some regularities that we have in the data that occur during the processing. And here you will see that when we calculate the pixel, or we want to calculate the pixels that we have to draw on a specific scan line, we can take advantage of the pixels, the knowledge of the what pixels we have drawn with the previous scan line. So let's look at one particular example. Let's look at the scan line number 3. Number 3 is this scan line here, and then we say we have this scan line intersects with two edges, and we call these active edges. So this, in this case, this is the left edge here and the right edge of the polygon. Oh, that is really bad. And that is also bad. So yeah, that looks better. So we have these two lines and we call them the active lines. And now, of course, it is intuitively clear that if we know the intersection points of the scan line with those active lines, we also know what kind of and if we know which is the left and which is the right one, then we also know what kind of pixels to draw, namely everything that is in between those two intersection points. So if we have this intersection point here, and this intersection point here, it's clear that we draw everything in here between. So the trick is now, the next step is now to find those intersection points. And if we look at, for example, at the left edge that we have here, which starts at 1, 1 and ends at 3, 8, then we can make an implicit equation of it, which is this equation here. So remember, the implicit equation was the ax plus by plus d equals 0, and the ab is the normal vector. So this is the normal vector ab. Or you can also write this, in this case it's probably a little more intuitive to write it in the slope-intercept form, which is y equals mx plus, let's call it d dash, because it's a different d than here, in the same way as the m is a different than the AB here, but you see if you transform this that the m value is basically a divided by minus b. And wasn't that even an exam question that you should show the vector to it? I don't know, maybe. Anyway, so yeah, I hope you remember that. If not, it's a good opportunity to repeat it. And if we, the slope-intercept form is in so far quite, later, sorry. If we look at now, if we want to have this intersection point, which is at the scan line number 3, then we see, of course, this intersection point, because it's at the scan line number 3, has the y coordinate 3. Because it's a scan line number 3. So if we put that in here, we get the x value, which is 1/4, and that means we start, since it's the left one, we start painting with pixel number 2. Remember, we moved it, so we're dealing with the pixel center here. So 1/4 is a little bit to the right of the center, which is why we start drawing with the second, and then we draw to the right till we reach this other intersection point, which we can easily calculate in the very same way. Good. So we know now how to calculate these intersection points and how to calculate how to draw, get which pixel to draw in between. But of course, it would be, I said we want to take advantage of this scan line, so we already have calculated the values for the scan line before. Now it's the trick is to save some processing time to take advantage of that result that we have. And if you think about it, if you have a polygon and it's like this, then the next step of the polygon can basically be anything. It has to be somehow connected. So this cannot be the next step of the polygon, of course, unless you have something like this here. But if you have in this direction, if you want to know what kind of pixels to draw here, this can only be something here or that moves a little in that direction. So you basically have to find these two new intersection points, but they depend on these intersection points, of course, from this line equation that we have from the line here. And this is then what we call this vertical coherence. So we look into how does this intersection point change based on the line equation and the previous intersection point that we have, instead of calculating it from scratch. And this is now where I think the slope intersection form is a little more easier to understand. So if you look at the slope intersection form, you have y is mx plus d, let's call it d dash again, and then you know the slope is defined as the if you draw a triangle here, for example, this is a delta y and this is a delta x, and the slope m is defined as delta y divided by delta x, and that is, in this case, for example, 8 minus 1 divided by 3 minus 1, so 7/2. It also works if you draw a different triangle, because then the x and the y, the delta x and delta y, they change, the relative change to each other stays the same, so the division of it leads to the same value. And now if we want to know how it changes when we go from one scan line to the other one, that means we change the delta y value by 1. So if delta y is 1, then if we set delta y to 1, then it's clear that the delta x is 2 divided by 7. So this is exactly the value that the x changes when the y when the scan line moves from one position to the next one. So if we have this intersection point here, then this intersection point has a y value that is 1 larger and an x value that is delta x larger. So in this way, we can easily, when we have the first point, which we don't need to calculate because that's a given one, that's the lower value of the edge, we can just have to calculate this delta x, and then we constantly add it to it and add the 1 to the y value until we reach the upper edge, and then we have all the intersection points, and we did not have to calculate the intersection points, but we just calculate this delta x once. So this is basically the idea of the scanline algorithm, and now we oh no, this is an example of what I just said, but it's pretty straightforward. We have the scanline, so this is the delta y, which is always 1, and this is here the delta x, which was 2, 7, so we have plus. What is wrong here? I didn't change anything from the setting. Anyway. So here it's always plus delta y, which means it's plus 1, and here it's always plus delta x, which means it's plus 2/7, until we reach the upper part here. So we continue this till we are at scan line number 8, and then we know we reach the upper edge of it, and then we have all the intersection points. So this is how we can do it. It's pretty simple to understand. The question is now how we do this, how we implement this efficiently. And the trick is to just use two tables. One table that basically is used to represent the polygon, and the other table which is used then to do the calculation, to do the processing. And the table to represent the polygon is called the edge table. And the edge table contains, for every scan line, a list of edges. So we have, for every scan line, that a list of edges that start at the scan line. So for every edge here that starts, we have in the edge, for the start of every edge, we have an entry in the edge table at the related scan line, which is basically the y. And the index of the scan line is the y value of the edge. So we have here an entry in the edge table for 1, 2, and 4, because these are the scan lines where an edge starts. In this case, actually, even 2 edges start, and also in this case here, which is why at 1 and 4 we have 2 edges stored. And here we store here something that we call an edge record. And the edge record contains the x-coordinate of the lowest vertex. So that's the y value. The scan line index is the y value of the lowest vertex. The first entry of the edge record is the x value of the lowest vertex. So that is in this case 1. In this case it's 4. In this case it's 9. So you see here 1, 1, 4, 4. And for the second scan line, when the second scan line starts, we get the edge with the x value at 9, or the vertex with the edge value at 9, with the y value at 9. And then we store the y coordinate of the highest vertex, which for this edge is 8. So we have an 8 here. For this vertex is also 8. So we have an 8 here. Then this vertex is stored here, and the y value is 6, so we have a 6 here. Same here, it's also a 6, and for this here it just goes 1 to the next scan line and it's over, so we just have a 2 here. And in the last value we store this delta x that we calculated based on the slope. So we already saw that in the first case it's 2/7, and for the others you will can calculate it yourself. You see, for example, here that the slope here is the delta x here is an 8, because if we move from 1 to the next y value plus 1, we have to add 8 values to the x value to get to this point here. And for the others the same. And if you think about it, this is a kind of an efficient way to store all the information that we need to describe a segment of our polygon, because we have stored the starting edge, the starting vertex by the scanline index and the first entry in the edge table. We have stored the second vertex indirectly by storing the y value and storing the delta x. And with the delta x and the x's, we get, of course, also the x value of the upper edge. So we have all the information here that we need to reconstruct our polygon. Now, to do the calculation, we use another table, which is called the active edge table. And the active edge table, you see already in the name, it is an active table. So this is the table that changes then, that does the processing. And for that, we start by initializing it with that the table initially contains the edge record from the edge table that intersects with the current scan line initially. And then, of course, in each step, this entry changes, because in each step we add, for the next scan line, we add the delta x value to the delta x value to the stored x value. So let's look at an example here. We see here we start by we take the record and insert the the edges that intersect with the current scan line. So of course at the beginning it's clear we start with this one. We have the scan line is here. So we enter the first entry at scan line index number 1, which means the y value 1 is 1, 8 to 7th, and the second entry is 1 to 8. Sorry. And then we move on to the second scan line, and then we see we have to add the delta x to the x value. So we get 1 to 7th here, to 8 to 7th, so the rest doesn't change. Then we get here 9 to 8. And then when we move to the third scan line, of course we get 1, 4, 7th, because we again add this here, plus delta x, same here, plus delta x, and the rest doesn't change, to 7th. But then we see also at number, here I forgot, here at number 2 we get another one that starts here, which is this here, 9, 6, minus 1/2. And if I add that here, I get 8.5, 6, minus 1/2. Now you see I left this one out here, but I didn't forget it. I did it on purpose because that segment here stopped, and we can easily see that because the index of the scan line is the same as the second y value, and this is why we store the y value, because it gives us an easy way to check when a segment is over, when we have reached this upper vertex. So we don't write it down here, and we only continue with the lines that are now active at the third scan line, which are these two here. But this one is done, so it's no longer active. And these we haven't seen yet, so our scan line hasn't seen those yet, so they are also not active, but they will be added later. So yeah, this basically summarizes what I just said, that we remove it from the active edge table when we reach the end of the edge, the top of the edge, and that means that when the second entry of the y coordinate is the same as the index of the edge table. So if we summarize this, and you see now then, the reason why we're doing this is that this gives us exactly then our intersection points here. This is then the x value of the intersection point, and this is the y value of the intersection point. And then we can draw all the pixels in between. So if we look at the algorithm, if we do it in pseudocode, we go through each of the scan lines, then we update the scan line, the active edge table. That is, we delete the edges that are where we are at the end. We add the delta x to the value to the others to get a new intersection point based on the previous intersection points. Then we add them. That's this here, and then we add the new edges that start at this intersection point. Then we put and then we draw the pixels in between all those intersection points. And this step, I haven't really said much about it yet. This is the where we sort the edges based on the x value. I already did this here implicitly. The point is, if we want to draw all the pixels in between the left and the right intersection, we need to know, of course, which one is left and which one is right. And we can easily know that by sorting them by the x value. And then, of course, it's clear that we start on the left side and end on the right side. And this is, I will not go write it all down because yeah, it's pretty simple and straightforward, but I have put it down here, so if you do it yourself, you have the solution here. You can compare it if it works out. And you see here, for example, this is the left edge where we have this 2/7, and this is increased here each step until we reach the 8, which is the same as here, which is then the top edge here. So these are all our intersection points here, and since these are always the first when we sort them according to the x coordinate, we know that this is always the left side of our polygon, and then the next one with the next highest x value is the right side. So in this case here, when we have only 2, of course the next one to the right is then also the final one. In this case, where we have a polygon that goes over two parts, then of course we have four situations here, four intersection points here, but then we know that this is the left, this is the right, this is the next left, and this is the next right. And if we have a situation where we have three, then we know this must be something where we have a situation like this, that we have this corner here. So we have three intersection points, but we know that this is not like a new or a situation like this. We know that this is not a new one, but we know that this is then we can just draw everything in between. Good. So in this case, we draw everything between this one, and here we draw everything between this one and this one, and we easily see that we don't have to consider the second one because it has the same x value and the same situation is here. Good. So that's pretty simple, pretty straightforward. I think it's just you need to do it a few times to get an idea about the processing. And yeah, so this way we can easily scan over a scanline and decide which kind of pixels need to draw. But scanline algorithms can also be used for other things. For example, they can be used to calculate the values for the interpolated values of the set buffer. You probably remember, or hopefully remember, that we had last time we talked about the set buffer, and I said that we can interpolate the values in between, and I think I also said I will tell you about a more efficient way to do this next time. So no surprise, this is the efficient way now. This is the scanline algorithm, because if you think about it, if you have a set buffer and you have a set value here, Z0, and a set value here, Z1, and you want to know now the set values in between, you can do a linear interpolation between them. That's what we already know. But a linear interpolation, if you write it down, it is basically the same as the equation for a line. And if you have the equation for a line, you can now calculate a delta set. And if you have this delta set, then you can use the scanline approach. So you can go move a scanline here up and can calculate all the and you can calculate all the values here along this edge, also along this edge, and of course then you can also calculate the values in between here. So you don't draw the pixels in between here, but you calculate the values, you interpolate the values in between by not explicitly calculating each value, but by just adding this, calculating this delta set once and then adding it to it. And then you can very efficiently calculate the values for your set buffer. And there is no surprise that I use this image where we also see this frame buffer here, because we can also use this, of course, for bringing some color onto our pixels to do interpolation with color values. And since this moves us to the next and final topic of today, which is shading, we make a little break here and then discuss this in the second part.